Hey everyone, in this video, I would like to talk about Ptolemy's theorem for cyclic quadrilateral for competition math. So I gotta give you the cyclic quadrilateral, right? So here we go. We get a circle. Ooh, that's a nice one. And I can give you some cyclic quad like this. And let's just try to label A and B and C and D. And if I just simply connect D and B, well, I'm going to find a certain point, but not necessarily the center, the circumcenter of this, like the figure, but I would like to find certain point such that if I perform rotational symmetry or rotational, I guess, dilation at the same time, rotational dilation, or, like the rotation and dilation at the same time about point C, we can actually get some similar figures such that if I find certain point, I would like to call this as E. Okay? If I find some point like this, then you can argue that these angle, and of course, I got to connect A and C all together such that those angles are congruent to one another because they are intercepting the same arc. And I'm going to argue that these angle is going to be congruent as well. That's a constructive geometry. All right, so I'm going to argue that DEC is similar to ABC. So here we go. We got DEC similar to triangle ABC. Okay, so here's what's going to happen. DE to DC, right? DE to DC, which is 1, 2 to 1, 3, equals AB to AC. Okay, so we get AB times DC, which is going to be the same thing as DE times AC. DE times AC. Right, so that's for part one. Now, try to check out a triangle BEC and triangle ADC, like this. And here's what we're going to do. Remember, the opposite angles for a cyclic quadrilateral are usually supplementary. And I'm going to argue that this angle out here, the angle that I just drew out there, is actually supplementary or forming a linear pair with this angle. And I know that this angle out there is actually corresponding angles of similar figures. So we know that these are similar. These are congruent to one another. So I can argue that the angle that I marked with the color, I would say, that becomes congruent to the angle D. And now we've noticed that this is going to be the common angle. So we get one angle out there and another angle out there. I can tell you that the triangle ADC is similar to triangle BEC. So triangle, write it down as ADC, is similar to triangle BEC. Good. So here's what we're going to do. AD to AC. AD to AC is going to be BE to BC. All right. So multiplying the inner parts and multiplying inner parts equals the product of the outer parts. So we get AC times BE, which is just going to be AD times BC. All right. So one at a time. We have AB times DC, which is going to be DE times AC. I got AC times BE, which is going to be AD times BC. So here's what's going to happen. Okay. So I'm gonna say AB times DC, which is going to be AC times DE, and I would like to switch the order of things that are being written. So if I write it down as AD times BC, well, this is just going to be AC times BE. And if you perform the vertical addition, like this, well, we get AB times DC plus AD times BC, which is going to be AC times BE plus ED. Now, thanks to something called segment addition postulate, and we know that D and E and B are in fact collinear, well, DE plus BE is supposed to be just BD. So we get AC times BD. All right, so here's how we have deduced the Ptolemy's theorem, or Ptolemy's formula. AB times CD plus AD times BC equals AC times BD. So the product of the diagonals actually equals the sum of the product of the opposite sides. And this is how we prove Ptolemy's theorem.